Hi, so welcome back. So we will continue our studies with group homomorphisms and normal subgroups. In the last lecture, we learned about group homomorphisms and we kind of got into what normal subgroups were. So this was the definition. So a subgroup will be a normal subgroup of G. This is denoted like this. It's a triangle to denote it like a normal subgroup. And just the less than equal to sign, for example, this one is just a subgroup. So this will be a normal subgroup if this condition held for this subgroup N, okay? If the subgroup was equal to its own conjugate by any element of the group G, okay? So a subgroup would be called a normal subgroup if it was equal to its conjugate by any element of the group G. Now, of course, if this is true, a lot of equivalent statements can be made. If this is true, then it can be shown that this is true. Okay. In other words, so this is viewing N as being equal to its own conjugate. If you sort of transfer this G inverse onto this side, and of course, you can't just do that because these are sets. So we have to take care of a lot of things, but you can in a way do that, and we can show that in that case this equation gets transformed into this equation, which if you look at it, this says that the left coset of this subgroup by an element G will be equal to the right coset of the group of the subgroup by the same element G, okay? So if a subgroup is a normal subgroup, then any left coset will be also equal to the right coset. Left coset by an element G will be equal to its right coset by the same element G, okay? So this is an equivalent statement. You can show this back and forth. If this is true, then this is true, and if this is true, this is true. This is necessary and the sufficient condition. Again, you can show that this is also true. Okay, it's really the same thing, except that now you are taking the cosets by the G inverse. Okay, and they're all equivalent statements. And you can also show that this subset or the subgroup will be equal to what this says is that the subgroup will be equal to its conjugate by G. What this says is that subgroup will be equal to its conjugate by G inverse. Okay, so here instead of G you have the G inverse, and here there's G inverse. There is G which is G inverse. Okay, so anyway, so these are all equivalent statements, and they're very easy to prove, and this will go into the assignment. But it's a good exercise to try out and see how things pan out, okay? So these are all equivalent statements. So to show, in other words, what this says is that if somebody wants to show that a subgroup is a normal subgroup, proving any of these is just good enough, okay? Because this would imply what the definition says, okay? So that's a statement that we will do as an exercise in the assignment. Now, one important thing is that if G, the mother group, so to speak, okay, if the group itself is commutative, in other words, you can multiply elements from, you can swap places of elements in a multiplication, and the product will remain the same. If it's commutative, then any subgroup will become the normal subgroup, okay? And that's just very evident because if you take an element. If you take, for example, an element GH from the left coset of H, okay, you see small h is an element of capital H. If you take an element from the left coset of H, then of course G is commutative. If G is commutative, then you can swap positions of this, okay. Then GH can be written as HG, okay. And then this becomes an element of the right coset of H of G. Okay, so this element, which was an element of the left coset, is also an element of the right coset. Okay, so therefore the left coset is a subset of the right coset, and by the same argument, the right coset will be the subset of the left coset, and so the two will be equal. And as I said here, if the right and the left cosets of a subgroup by an element is the same, and this is true for all. If this is true for all G's, of course, this is true for all G's because capital G is commutative. It means that any small g will happen. So the left coset. So if G is commutative, the left coset will become equal to the right coset for all G, and that would mean that it's a normal subgroup by this definition, by this implication. Okay, so this is a very strong point or a strong character to have. If G is commutative, then it's a property, not a character. If G is commutative, then any subgroup will become a normal subgroup. Okay, so yeah, and also now there's another statement which is something that we have actually done for the kernel, which turned out to be a normal subgroup. If n is a normal subgroup of G, we can show that this will be a normal subgroup. A subgroup will become a normal subgroup if the conjugate is a subset of the subgroup itself. Okay. If n is a subgroup of G, and if you can show that the conjugate of n by any element of G is a subset of n, then n becomes normal. And this is something that we have shown for the kernel, and exactly the same proof happens here as well. Okay, if this statement is true, that a subgroup always contains its conjugate by any element in G, then n becomes normal. And this is the proof that we have done where n was k and everything else in the proof remains the same. This was done in the previous lecture. And also this is true, if it is given to you that n is a normal subgroup, then of course the conjugate will be contained in, because the conjugate will be equal to the subgroup. Okay, normal means this holds, and if this holds, then the conjugate is always a subset of n. So this is true, the necessary condition. In other words, this from this to this proof is just plain and simple from the definition. This one to this one, or the sufficient condition, was the one that we had already done with k instead of n, and the same argument holds. This is just so kind of a recap, but also a generalization. Okay, right. So with this setup, this is kind of a recap. With that has to be verified. We will do that in the assignment. We come to it's a new concept, what we call the quotient group of G by a normal subgroup of it. Okay, what that means is, suppose n is a normal subgroup of G, you collect all the left cosets. You can collect the left cosets, you can collect the right cosets, doesn't matter because they're equal once n is normal. Okay, we will work with left cosets just as as a choice. And so if you collect all the left cosets together in a group, or in a set, not a group yet, okay? If you collect all of them together and you give it, well, there are two names that are normally given to them. One is G. This is the notation for quotient, G quotient by n, okay? Or sometimes, because the writing becomes a little complicated, so people just write it as G bar. It just means that it's a collection of all the left cosets of n, where n is a normal subgroup of G. Okay. Now remember, one important thing, and this we have learned while doing the Lagrange's theorem, the proof of the Lagrange's theorem in the assignment, that not all left cosets of a subgroup will be will be different. In other words, some of the left cosets will be equal, okay, and those which are not equal will be absolutely disjoint or disjoint sets. So really, what left cosets do is that they partition the group as a set, okay, and that really was the crux of the proof of Lagrange's theorem, that left cosets, if you think about this group as a set, what left coset does is, or cosets in general does, is it sort of partitions the group as disjoint subsets, okay, where this is some left coset, this is some left coset, this is some left coset, okay. If you take any random left coset, it will be one of them, okay. This is the disjoint or the distinct set of left cosets that you can find in a group, okay. So when I say collect all the left cosets of G, or left cosets of N in G, this will definitely not have the same cardinality or the same number of elements as G. Some of the left cosets will be equal and some of them will be absolutely not equal, in other words, disjoint. Okay. So, and the condition that we have learned, this was done in the proof of Lagrange's theorem in one of the parts. The condition which actually guaranteed when two left cosets would be the same was this condition. Okay, the two left cosets, G1n and G2n, this is the left coset of n by G1, this is the left coset of n by G2, where G1 and G2 can be different elements of capital G, but the two cosets will become equal if this was an element of n. Okay, if G2 inverse G was an element of the subset of the subgroup n. Okay, also G1, there's a G1 here. Okay, it's the other way around as well. This, the inverse could be here as well, and still the condition would hold, but it doesn't matter. So this was the condition, that when two left cosets would be the same. If this does not happen, then the two left cosets would be not only not equal, they will be absolutely not equal. In other words, they would be totally disjoint as subsets. Okay. There's another notation that is used sometimes for convenience. Gn is not normally is normally written as G bar sometimes, just for convenience in writing. In this case, in this notation, this argument is written like this, where G1n is written as G1 bar. It means that it's the left coset of n by G1 will be equal to the left coset of n by G2. If and only if this combination of them, G1 and G2 as elements, if this is an element of the subgroup N. Okay. All right. So this is basically a recap. Okay. Coming to this point, this was the definition. So if you collect all the left cosets together, that would be called the quotient of the group G by the normal subgroup N. And any of the two notations can be used. All right. Now, once we form this new set, it's a set of all left cosets of n in G, we define a binary operation on it. Okay. These are, as I said, these are all the set of all left cosets, the set of all left cosets. We define a binary operation which I denote here by star. You can denote it by anything, as is evident now that we will omit sometimes, or most of the times we will omit the binary operations, and once we understand in which group we are working. Okay, but anyway, let's denote it by star. So this is a binary operation from the quotient group, this product of quotient groups to the quotient group. By this definition, okay, where if you take the binary operation on two elements of G bar, the quotient group, suppose two elements are G1n and G2n, or in the other notation is G1 bar and G2 bar, then the product by the star, or the binary operation, is defined as you take the G1 and G2, which are elements of capital G, which are elements of the group, you product them like you would product in a group, with dot as the group. If the group had dot as its binary product, you take the G1 and the G2 from these two elements, you product them like you would product them in a group, and then you take the left coset of n by that new element. Okay, so that's the binary operation that we're defining. Take two elements of G bar, which will be two left cosets of G, left cosets of n, one by G1, one by G2, let's say. then the binary operation, is just taking the product of G1 and G2 in the group and then taking the left coset of n by this new thing. Okay, so that's in this notation, it's written like that. G1 bar product with G2 bar with the star as the product will be equal to G1 G2 as element in the group, G1 dot G2 that is, and then the bar means taking the left coset of n by this element. Okay, all right, so that's a binary operation that we define. One of the moment we have a set and we have a binary operation on it, the inclination is to check whether that binary operation makes the set a group or not. Okay, and that's what we are going to see. So I'm skipping this 8 just for a moment. So once we define the binary operation on this set, the quotient group or quotient set by n so far, once we have this new thing, then this quotient set by the normal subset n, and we have the binary operation on it, the inclination is to check whether this will turn out to be a group or not. In other words, it will satisfy the 4 axioms of being a group. It will be true, and we will show it today. This is true. This set with this binary operation will become a group. But before that, there is something that has to be checked, that is the validity of this binary operation that we have defined. So why do we need to check the validity? And that's point number 8. And it's written in mathematical terms, it's called whether or not star is well defined. So the reason why we need to check the validity or the well-definedness of the star is this. Because of exactly this reason, that the 2 cosets may sometimes become equal. Okay. In other words, if you take G1, if you take a coset, if you take one coset from this element, from this set, okay, this contains all the left cosets of n. If you take a left coset of n, it can be the left coset of n by G1, or it can be the left coset of n by G2, for example, and the 2 can be equal. Okay, so what I mean is that this one, G1 and G2 that I've written out here, they're really the representatives. Okay, if G1 and G2 are in this special relation where G2 inverse in G1 is an element of the normal subgroup, okay, or just subgroup in this case. If G1 and G2 are such that this is true, then we know that the two left cosets, one by G1 and the other by G2, will be the same. So if I take a left coset from this set, what's the guarantee? Or I can represent it as G1n and G2n if I can have 2 elements, G1 and G2, which follow exactly this particular condition. Okay, so this left coset can have 2 representations. It can be written as G1n and it can be written as G2n, and the 2 will be equal if the G2 and the G1 that I'm talking about actually follow this condition. Okay, so when I say take a left coset from here, I'm not really, I'm not instructing as to what the representation of that left coset would be. Somebody is free to call it G1n, somebody is free to call it G2n, and the 2 will be the same if the 2 people calling G1 and G2 follow this thing. Okay, so taking a left coset really gives us, saying that take a left coset gives us some kind of there is some ambiguity as to what would be the representation of it. Okay, people can choose their own elements, G1 and G2, to represent that left coset by, okay? As long as the two G1 and G2 or G3 or G4, whatever, okay, there can be many representations. This could be, somebody can take G3 n, and G1 and G3, if they're also in a condition, in a relation like this, which, this thing belongs to n, then these two will be equal. So when I say take a left coset, it's not clear as to what would be, how people would represent it. If people can choose their own elements, G1, G2, G3, G4, and then write it in, according to their choice. And all of them will be equal if they're picking the right elements. In other words, if elements were following this condition, then all of the left cosets would be the same. So that's the problem here. So what I mean here is whether or not this is valid. If somebody takes, I'm defining the left coset, I'm defining this binary operation on two left cosets, which by choice I have picked the first one as G1n and the second one as G2n. What if somebody chooses, or because I've written G1, G2 like this here, let's make this 3, okay? Forget this 3 over here. Let's not complicate things too much. So suppose I'm basically defining the binary operation on two left cosets, which by choice I have taken as G1n and G3n. And I've defined it like this, as I have already mentioned. What if somebody says that I will not write this as G1n, but I will write this as G2n? Because when they say that they want to write it as G2n, of course that means that G2 inverse G1 will be an element of n. Okay, so if somebody can find another element G2, whose inverse product with G1 is an n, then that person is free to call this G2n. You see that? That's what this means. Okay, I'm calling it G1n. Somebody finds an element which sort of, which products with, somebody finds an element G2 whose product of the inverse with G1 belongs to n, then that person is free to call it G2n. So this is a choice, matter of choice. Somebody else calls it G2n. I'm calling the second one G3n. Somebody else finds another element such that G4 inverse G3 is in n. Then instead of calling it G3, instead of calling this left coset G3n, that person is free to call it G4n. So in other words, calling it G3 bar and calling it G4 bar is the same because they have this relation between them. Okay. So the question is about terminology. I'm calling this G1 and G3. Somebody else is calling it G2 and G4. But of course, G2, G1, and G3, G4 are in the special relationship. That's why we are able to call it by different names. But we really mean the same left cosets. So by my definition, or by my choice of naming, this product becomes G1, G3. By their choice of naming, this product should become G2, G4. Okay? And that's the... Sorry, this is... Yeah. So according to my terminologies, this product will be, or this end product of this binary operation will be G1, G3n, or G1, G3 bar. By somebody else's terminology, this should be G2, G4 bar, because G1 and G2 are the same, and G3 and G4 are the same bar. Okay. So the question is, if this is true, that my G1 and somebody else's G2 is true, and my G3 and somebody else's G4 are true, will our two products be also the same? In other words, G1, G3 bar, will that be equal to the G2, G4 bar? In other words, this is my definition of the binary product. This is somebody else's definition of the binary product. Will the two definitions be the same? That's the question. Once this is true, this will become well defined. And this is something that we have to check. Because of this, there is ambiguity in representation. Okay. Well, let's just check that quickly. Once that is checked, in other words, once this becomes valid, this becomes a valid binary operation, then we can go on to check whether or not this is a group. Okay. So let's do that. Suppose this is true. This is true means this is true. This is true means this is true. We just have to show that these two are equal. To show that these two are equal, there are bars over here. To show that these two are equal, we just have to show what? We have to show that G2, G4 inverse G1, G3 is an element of N. That's all we have to show. Is this correct? To show that these two are the same, we just have to show that G2 inverse with G1 was an element of N. So to show that these two are equal, this inverse with this must be an element of N. This is what we have to show. And we know that this is true. Okay? Because these are true. So let's try and show this. This element, so we have to show that this will be an element of N. Let's see. The inverse on a product will become G4 inverse, G2 inverse. The position swap, okay, once you take the inverse in. And then there is the G1 and G3. Well, we are working in a group, so I can take my own groups of or own brackets just because associativity is true. And what about G2 inverse G1? Well, that's an element of the subgroup. This is a normal subgroup. Remember, this is a normal subgroup of G. This is an element of N. So let me give it a name. Let me call it small n1, this whole thing here, G2 inverse G1 and G3. Okay, let's do something more. What about making G4 inverse N1 G4 inverse G3? Is this true? I'm just in between N1 and G3. I'm just squeezing in this thing here, which really is the identity. It's G4, the same G4 product with its inverse. So that's really the identity. Okay, I'm squeezing in the identity but written like this. And then by our power of associativity, I can bracket out different groups of elements in this product. Remember, this G4 inverse G3, well, that's another element of N. Let me call it by some other name. Let me call it N2. So this is N2. And what about this? G4 inverse N1 G4. Well, remember that N was the normal subgroup. So N normal would mean that it's equal to any of its conjugates. So if I conjugate N by G4 inverse, this should be equal to this. It should be equal to its conjugate by G4 inverse because it's normal. And remember this, look at this. What is this? This is an element of this conjugate because small n1 was an element of capital N. So this is the conjugate of this element by G4. This is the conjugate of the total set. This is an element of this. And because this set is equal to this, so this must be an element of N. Is that clear? This is being an element of this and this being equal to this as a set. This has to be an element of N. And let me give it another name, N3. Okay. So therefore, this is N3 and this is N2. That's a product of two elements in a subgroup. That's a subgroup. It's a normal subgroup. So closure property holds. So this obviously is an element of N, and that's what we had to show. We had to show that this was an element of N, and it's true. So therefore, and that's what we wanted to show that my definition would be equal to somebody else's definition if they named the left cosets differently. I call them G1, G3, they called it G2, G4. And so it's true. So my definition would be equal. So therefore, this is without ambiguity now. Okay, now this is valid. It doesn't matter who calls it what, our definitions will all be the same. Okay, so therefore we can finally go on to check whether or not the set of all left cosets of G by N, along with this product, whether or not this is a group. So let's check that quickly. It's not difficult anymore once we have established this. Now, the closure property, well, that's just evident from the definition of the binary product. G1 bar star with G2 bar was G1, G2 bar. It just meant that because G1, G2 was an element of capital G of the group, taking the bar means taking the left coset of N by this element. Of course, that's an element of capital G bar, which contains all left cosets of N. Okay? Or maybe it's better if we wrote it like this. This was G1, G2, N. By definition, this is an element of the left coset. This is a left coset. This is a left coset. In other words, element of G bar. Because this is also a left coset by this element G1, G2. This is a left coset, so it must be an element of G bar. So the closure property holds from the definition of star itself. What about associativity? That's always true. But let's just show that. I think it would be not very difficult to show. I'll use the bar notation here. I hope we're clear with it. This bar just means that taking the left coset by that element. This would be first of this product. In other words, I product G1 and G2 in the group G. Then I take the left coset of N by this. With G3. It means that I product this element and this element. So I take G1, G2, G3 as an element in G, capital G. Then I take the left coset of N by this element. Okay. Similarly, if you go around from the other side, if you go around okay, I think it's pretty clear that by the same logic, first you will have G2, G3 here, and the G1 will be, standing outside. And then by the same way, you can product that in, and it becomes the same. So associativity is true. What about the identity? What's the identity element? Well, this is a very special element. The N, which is a normal subgroup, and it is also, it can be written as a left coset as well. Left coset by the identity in the group G, which I'm calling I, of course, or 1. Okay, so a subgroup. So again, this is really the matter of choice. Okay, how you want to call it. If you want to view it as a subgroup, that's fine. But somebody else may view it as a left coset by the identity element, and the two will be equal. Why? Well, that's very evident. If you multiply 1 into all the elements of N, you would just get N. Okay, so I think we don't have to say much about it. It's just how you look at it. Okay, you can look at it as a subgroup. You can look at it as a coset. Okay, so this subgroup itself, which happens to be a left coset by the identity element in G, this is an element, therefore, this is an element of G bar, because N, which is a subgroup, is also a left coset of N by 1. So therefore, it's an element of G. And this will be the identity element. And I think that's true. If you take some element from G bar and you product that with 1N, the identity in G, then you would get G with 1 and the coset by this element, but that's just G. Okay, so sorry, I have taken G1 here. So really, this has no effect on this as far as multiplication is concerned. Okay, it multiplies to keep the element as it is, and you can do it from the other side as well. You will just get 1 on this side. So the identity holds. This is the identity. N is the identity element. Okay, right. So you can just write it. So the identity in G bar is really this element N. Okay, what about number 4? That is the last one, which is the inverse. So if I have some element from this from this set G bar, which obviously is a coset, can I find something? Can I find another element H, another element from G bar? In other words, another coset of N, okay, such that Gn multiplying Hn gives me the identity, which is N. Can I find this H? I think that's very easy to find. If I just take the inverse of this element, then what you get here, you would get G with G inverse and taking the left coset of N by that. Of course, this is 1, and we have just shown that 1N is N. Okay, so that's it. So because this is the identity element, for an element in this set, which is a left coset, you can find the left coset by the inverse of G. And if you product it by the star, you would get the identity in G bar. And so therefore, this is the inverse of this. Okay, and that proves all the axioms. And therefore, G bar, which is the quotient group, or quotient by the normal subgroup N, that turns out to be a group by this binary operation, which we had shown to be well defined. Okay, so that's it. And lastly, just one important thing that I will just finish with is just a last statement. Is once we have established that G bar star is now a group, I can talk about homomorphisms from this group, the original group, and this new group that we have found, this group where all the elements are cosets of N in G. Okay, so this is a new group that we have found, which really we have carved out from the mother group here. But because it's now a group with this operation, and this was already a group, we can talk about homomorphisms between them. And one obvious homomorphism is what I'm calling pi, or the projection homomorphism. The projection homomorphism. What I mean by that is the definition of pi would be, if I take an element from G, I'm just going to give N G bar. In other words, the left coset of N by this element G. Of course, that's an element of G bar. Okay, so I'm just going to call it the projection operation, the projection homomorphism, and we can check that it's a homomorphism. Pi on G1 G2 will be G1 G2 bar, and we know what that was. By definition, it was G1 bar star G2 bar. Okay, that was a definition of star. Okay, and this, so therefore you can see that pi here, it takes a product of two elements from product means with the dot here, and it breaks it up. Okay, this is of course pi of G1 star with pi of G2. Okay, so therefore this is homomorphism. Pi is a homomorphism. It's called the projection homomorphism. The important thing to notice here, and again this will go in the assignment, is once you have the projection homomorphism, we can ask about the kernel of this homomorphism. What would be the kernel, which will be a subset, actually a subgroup of G. The kernel of this homomorphism will be N itself, that normal subgroup. Okay, the normal subgroup itself will be the kernel of this projection homomorphism. Okay, so in other words, what we see is something very important. We had shown in the previous lecture that if we had a kernel of any homomorphism, this was a normal subgroup of the domain group. Okay, and if we have a normal subgroup, then the normal subgroup becomes the kernel of some homomorphism which we have just defined as the projection homomorphism. So given a kernel, it was a normal subgroup. Okay, and given a normal subgroup, it will be a kernel of some homomorphism. So that's a very important result here. Okay, which I can just write down as a very important statement is we can call it a theorem if you want, that a subgroup H of G will be normal if and only if that subgroup is the kernel of some homomorphism G. Okay, if it's and we've just shown it. Okay, if it's normal, then it will be a kernel of some homomorphism pi, and we have shown previously that if it's a kernel, then it will be normal. So it's a if and only if condition, necessary and sufficient condition, and we have actually proved this really, really important and amazing theorem. Okay, I think we will finish this here. A few of the sums will go into the assignment and take things forward in the next lecture. Thank you.